And what we'll be learning about today, neural networks, and more specifically, all the different types of hyperparameters to consider when you're training and evaluating neural networks. We'll go over one methodology in particular, how to optimize for those hyperparameter values, and we'll talk about how you go about the training process. So what does backpropagation means and the gradient descent method. Neural networks, really popular type of classifiers. They'll complement what you've already learned, learning about decision trees in the 2 weeks ago. And I won't talk so much about the details for radial bars and radar charts. I'll show you a quick example, but all the code is annotated in the slides if you do want to take a look. I think we're up to the point where after seeing like 4 different kinds of graphs, you get a feeling for how to create like a 5th one. So in terms of covering different kinds of examples, I think we can just leave it at that. What I'd like to focus on in terms of the coding for this week is how to deal with form inputs. So we'll elaborate a little bit more about like extra examples of event listeners. We'll start talking about routers as well as controllers. So setting up functions where you take the input from forms and then you do something with that input. In our case, within the dashboard, it'll be like hiding and showing a different part of the interface and then taking all the input values that we'll gather from our forms to do something like generate a prediction. So within the next few weeks, we'll start. So I'll have like trained like an example of all the models that we'll have covered to the course, like an example of a decision tree, a neural network, and then a naive Bayesian classifier. And then we'll talk about how do you implement that in JavaScript. So you can deploy your model within the dashboard, allowing users to type in input values for the model, and then seeing what is the prediction that you get. So a nice way to make your models available to all the end users, so everyone who would have access to your dashboard. So with that being said, working with JavaScript to handle form inputs. So we'll do 4 steps. First, creating a drop-down menu, and then we'll assign that to a variable in our JavaScript. We'll have to listen in for selection events that are tied to that drop-down menu, so whenever the value changes. We'll use a function to set up a router, so a switch function to evaluate the value of the drop-down, and then we'll call upon a specific function for each possible case values. So our drop-down will have 4 different values. So either you have just like a baseline classifier using a majority class, decision tree neural network, and naive Bayesian, and so we'll have specific functions that are tied to handle all of those different options. So again, if you want to follow along, you can download all the code example directly from the GitHub website. And when you open the index.html, and that would be for the week 7 module, you'll see the following example below. So this would be an example of a radial chart. Sorry, that's the radar chart. Next to it would be the example of the radial chart. And so we'll use the radar chart mostly just for displaying the errors of each model. So we'll update those values as we build models. You'll notice at the very bottom I have a form, a drop-down menu. You can choose between like majority class, decision tree, whatever model that you want to use to generate predictions. So after you click on this, what will happen there in future weeks is just like the graph will disappear, and then you'll see the form appear where you can add in your values. Over there to the right is once you click on, hey, predict something, you'll see the prediction results being displayed in the radial chart over here to the right. And so I'll just list the likelihood of that particular observation with a set of input parameter values, either falling under the survived or died target classes. And we'll have like a little message there at the bottom that explains those predictions that we'll update as well. But I won't go over all the details for setting up both of these charts. We have, at the end of this week, our activity number 3 to worry about. And for activity number 3, which I'd like to spend some time on this week working in class, so that way if you have any questions. So that will just entail creating either a new chart for a nominal attribute or a numerical attribute, and then listing it here. So if you want to get started in class today to complete that activity, download the week 7 course materials, and then just add in an extra chart using RapidMiner to generate the descriptive statistics that you'll need in order to add in those values. So we'll spend a little bit of time before next half of class to get some work done on that. But I did want to show you at the very least how to set up that drop-down menu and how to get the value that the user selects over here before moving forward for next class. So that's what we'll be working on today. So I'll just resize some of this here, and then I'll bring over brackets so we can take a look at some of the code. And again, I'm looking at the week 7 course materials. Got index.html open. You can close the data.js, so that would be everything relating to the graphs. But again, for all the details on that, I mean, I've annotated like all the little bits and pieces of code with the hyperlinks pointing to documentation, so you can just look at it on your own time. So I'm going to scroll down here in index.html right up to about line 100 and odd. Let's look. I think it was like 150 or something. I'm going to resize that so you can take a little bit of a better look. I apologize for the lag. Looks like we'll have to kind of bear with the computer today. Alright, and let me scroll a little bit more upwards so you can see the section where the drop-down menu was created. And I'll highlight everything that pertains to that form element, and I'll just delete it so we can start off from scratch. So I'll just show you from the ground up how that was built. So deleting the form, and in fact I'll do the same thing for the main.js. I'll just delete like a bunch of code that pertains to the event listener for that dropdown. But if you've downloaded all the course materials, you should have access to all of the code. But you know, if you just want to hang back and listen in, I'll kind of explain how everything kind of works together. In fact, I'll just save this, save that, and now what I should have here in my index.html is again the radar chart, the radial chart, but no drop-down menus here at the bottom. So that we'll have to recreate since we just deleted it. So going through those motions, so if you go to the model simulator section and take a look at the card header where it says model simulator, so that's the section that we want to create our drop-down menu. And in fact, we can create it right below the div container that has an ID attribute value of chart 3. Chart 3 just being used to create that radar chart. So right at the bottom, you can add in a form element, which is pretty standard when creating a form with some inputs. So that would always be the first step. Second, create a div container. And the Bootstrap 4 framework relies on a class that's called form-group in order to create sections. The div container will take just about as much width as the actual form element. The form element, again, is a block element, so it'll take about as much width as you allow it to. And every form input sections, according to Bootstrap 4 framework, is always organized in distinct form-group containers. So the form-group just adds in like a little bit of margin at the top, at the bottom to separate them. So not much. For more details on how to work with forms actually using the Bootstrap 4 framework, I mean, we'll cover quite a bit of examples in this class, like all the kinds of inputs like text boxes, sliding bars, We have multiple choice options, checkboxes, so a whole bunch of them. But I've also added the hyperlink to the relevant section of documentation for the Bootstrap 4 framework, so do take a look. Working with forms, something that you would do quite a bit throughout different kinds of projects. So if we're going to create an input, we have to create a label for that input, just a little bit of text to tell your user what's it about. And labels you can create for drop-down menus just using the label attribute. You can add in the label element, and then add in a for attribute with value. The value is really arbitrary, it's up to you to define, so drop-down dash model in this case. And then you can add in within the opening closing tag just a little bit of text for your user. In this case, select the model. And that'll prompt them to choose one of the options from the drop-down menu. So once we've defined our label, we can add a select tag. Inputs again are styled through the Bootstrap 4 framework. So in this case, there's a form-control class that you can bring in. And that'll do some basic things like, again, adding in some margins, but also defining the border of the drop-down, so it kind of looks neat. The important thing to notice here is that the ID attribute value for the select element should be the same value as the for attribute value for the label. You'll see that both of these actually match up. So drop-down dash model in both cases, and that just tells the web browser that that label associated with that control. Now within the opening and closing tags for the select element, you can add in all of your options, which is about how many different kind of models that you want to bring in your dashboard. Just as long as the labels are kind of intuitive enough so that your user understands what they're selecting on. So in this case, majority class. And we have quite a few. So next one is this is the decision tree. I do apologize here for the latency because the lag is just killing me on this side. Clicking right and waiting, and yeah, okay, so neural network. In the remaining weeks, we'll kind of focus on that part of the dashboard in particular. Just adding in like more form inputs for all the different attribute input values that you want to handle. And just writing in the code for all of these different models that you want to implement in the dashboard. So we should have all of our 4 options there. And if we could take a look at the website and refresh, at the very bottom should appear our dropdown. So again, the drop-down is styled using the Bootstrap 4 framework. So you'll notice once you select it, it has like this little blue highlight there just added in by default. That we can play around with the CSS code to change. Also adds in some border, all the margins is already handled. So for all those different styling options, take a look at the Bootstrap 4 documentation for how to handle those. Right now, you can choose amongst all those different options. However, once a user actually updated the chosen value in the drop-down here, so the actual value isn't actually used within the code. So to use that value, so we have to go to the JavaScript to actually add in first and foremost that drop-down to a variable that'll serve as like a container for it. And then we have to associate to it like an event listener so that we can actually listen in for when the value changes. So in order to first assign that HTML element to container, we'll need to select the element from the HTML. And in the case of a drop-down menu like this, you can go right to the select element and then use the ID attribute value here, which would be drop down dash model. So that I'll actually copy paste, and then I'll open the main.js document. So here from the previous week, we have a few things there. Mostly the event listener for that settings button in the navigation bar. But we can add in a new variable called drop down dash model. So that will be our container for the drop down model, for the drop down menu. So using the document object, and then our get element by ID method. So we're kind of keeping it easy. Always the same method to target your HTML elements. Add in a string that corresponds to the ID value of that HTML element. So in case drop down dash model, and then close that off with a semicolon. So we can save and then add in a console.log statement just to test if that worked properly. Drop down dash model, adding in the value of that variable. And so if that worked properly, I should be able to now, when I refresh the website, go to my developer tools. Within the console, I should see one of the HTML elements being listed, being my dropdown. And it's right over here, so that select element with the ID of dropdown dash model, which has all of my options. So as you're adding code, always a good idea to kind of log those things to the console just to make sure that everything is working properly. If it's not, then you'll see that it has like no value assigned, and then you can start troubleshooting. So next step, we'll be adding in our event listener. So we want to listen in for when the user changes the value of that dropdown. So if you type in dropdown dash model to define your variable, and then using the add event listener method, you'll have to define the type of event. I think in the course materials I added in click as a type of event, but you'll actually get better results if you use change. Change meaning a change in value, because it gets triggered a little bit more often. It's more sensitive than the click event, especially for that kind of like interaction with that particular like input. Change will get fired, for example, if you use like a text box. It's the minute that you click on any of the keys on the keyboard. So you'll have like change events that are detected. For drop-down values, it would be like every time that the user actually like the option that's like portrayed in the box actually like changes. So it's a pretty reliable event to kind of use for our event listener. So once you've defined your type of event, call in your function, opening, closing curly braces over here, close that off with a semicolon. And here we'll create a new function that's called router. So you can type in router, and within the parentheses for that function, we'll just send along the name of our variable for the drop-down menu, and then we have to get the value of the drop-down selection. For that, there is a method that's just called .value that you can bring in. So here we're calling a function called router, passing that value to the function, so you'll have access to it within the function. The value will be the string of text that the user actually selected, so it might be like decision tree or majority class or neural network, depending on their selection. But here we're just calling the function, so we actually have to define the function later on in our code. So to define your function, so you can just scroll down a little bit more here within your document, and then use the function statement. Type in the actual name of the function that you're calling. So you'll notice router here identical to the one that we're using to call the function, so it has to match. Opening, closing parentheses, because within these parentheses, we can define a variable that will store that information. So it's kind of like we're passing the value down to the function. The name of that variable, actually, you can call it what you want. So it might be, in our case, view dash update dash request, as long as it's something that's like intuitive. In our case, like, hey, you know, you'll have to like update the view for this particular model, like decision tree. So opening, closing curly braces for your function. And just to see how that's working, let's log to the console the value of that variable. Update dash request. So if this is working properly, every time that the value changes for the drop-down menu, it'll be passed here as a parameter to this function, so router. And then I'll just log the actual value that was passed using my variable that stores it, so view dash update dash request. So now if I go over here, and I think that got refreshed, but I'll just refresh it just to make sure. Here. And we open developer tools. And I'll just kind of keep an eye there on that console. So every time that I go down here, and then I choose, I click on router, the drop-down menu. So this is why you're not using the click on option. You can kind of use it, but sometimes I've noticed that some of these like selection events won't actually be registered. So using the change event in that case a little bit more reliable, just to make sure that you're actually detecting every time that the value changes. So if I click neural network, so the value is actually passed to the console. So again, you have to imagine like the event listener here, so listened in for a change in the value for that drop down, passed the actual value that was selected within the router function. The function here is defined there at the bottom. The value that I selected is assigned to that variable. So view dash update dash request, and now we're just logging the value to the console. So it's a little bit much to kind of keep track of, but that will allow you to kind of register every time that the user clicks on one of those options. It'll just send it to that function. And routers are kind of like the main function that manage like a lot of the events. They're usually used to like update user interface components, like the views that the users can actually see. So in our case, what we want to do is like when the user selects a different type of model, we want to update the view. So instead of showing the graph, we want to show like all of our form inputs so they can actually start typing like the values that they want to use to generate a prediction. Oh, it is on my computer. I have a touch screen. Still registering. Pretty fail safe. I think it would also work on phones. Surfaces have pretty much like the same event. I think that's associated when you click on the screen as like the phone, but it would be worth testing. Like if we change it to like something like a click. Save. See, that's what used to happen. Like the minute that you click on the control, registers as the event, which you don't want in that case because you want the user to allow the user to make a new selection. I think that was the only reason why that particular approach, that particular type of event was not like optimal. Yeah, I'll just register event like whenever you click on it. but I think the click also, like when you have it in focus, let's see, no keyboard events, but for drop down selections with like your finger and stuff, it still works. Any other questions before we talk about the switch statement? Okay, well, routers. Next step towards creating a router is creating a switch. So you just type in SWITCH, and then opening, closing parentheses, opening, closing curly braces. And what a switch statement allows you to do is to evaluate for multiple values that you list within the switch statement. So for the switch statement within the opening, closing parentheses, you have to pass a certain value that you want to evaluate. In our case, the value of that variable, because you don't really know what it is, but we have to check for all 4 possible cases. U-update-request. So to evaluate for a certain value, you have to define a case for that value. And then using a string of text, just list the value that you want to evaluate against. So in this case, majority class. If the value is the same as that particular case, then you can define below like a block of code to execute. Once that block of code has been executed, you can add in your break statement, which will pretty much like break you like outside of the switch statement. So the case has been met, you've executed that block of code, hits the break statement, and then you have to imagine like it just jumps outside of the switch statement. It doesn't evaluate all of the other possible cases. So here we can just list all of our case values that we want to evaluate against. So decision tree. Next one will be neural network. There's always a default option as a fallback. So if none of those values were matched, which is not very likely in our case, you'll just go to this fallback option, which in our case will do nothing. So let's see. Now that we've created all 4 cases to evaluate against, once those cases are actually met, you probably want to call some function, but a different function in each and every case. So we'll have 4 different functions that will all handle the input parameter values when the users complete the form to generate different predictions. So one function for the majority class model, one function for the decision tree model, another for the neural network, and then the last one for the naive Bayesian model that we'll cover at the very end of class. So let's see. So we can just call those functions. And we'll kind of revisit these and refine them a little bit later. But for now, we'll just kind of call them model-majority class, model-decision tree. Network. And they won't take any values for now. we'll kind of add that in a little bit later once we've created all of our form. So again, when you're calling a function, don't forget to define that function, otherwise it will throw an error. And to define our function, using the function statement, just add in the same value here, majority class, as the function that you've called previously above. Opening, closing parentheses. In this case, nothing will get passed within the function in terms of values, but we'll just log a little message in the console just to see if that worked properly. And we'll just repeat that for every function that we've listed in the switch. So logging a message for this one. For the neural network. And within each of these functions, so what we'll do is we'll write up the code once we get the export and wrap miner for the model. So that way we can deploy the model on the front end, and a little bit later in the course I'll show you how to also deploy that model on the back end. So there's different ways of going about like deploying your models to make them available to your end users so that your platforms can generate these kinds of predictions. This being the simpler way. Come on, function. I apologize again, the lag on my machine is just terrible. So, if this works properly, what will happen again, just to reiterate, adding in our drop-down menu as a variable, listening in for the change event for the value. We've called a function that's called router, and then passed the value of that drop-down within that function. So scrolling down to our router function over here that we've defined, the router function takes in the value of the drop-down that's assigned to a variable that's called u-update-request. So we're logging that value over here. That same value is sent to our switch statement. The switch evaluates for all possible cases of values. So if the value assigned to that variable matches majority case, for example, it'll call this function, and then it'll break, and we'll go outside of the switch statement, and then it's pretty much done. If the value, however, matches decision tree, so we'll call a different function called model-decision tree, and then so on and so forth, evaluating for all case values. Scrolling down over here, those different functions, they just log different messages to the console. So that way, if I open my web browser and then scroll down to the drop-down menu, let's just refresh the browser over here, and then we can maybe get rid of all these little console messages by refreshing it here. Clear the console. So if I scroll down, and then from my drop-down menu, let's say that I click on decision tree, so it should log the decision tree value that got sent to the router function, but it also logs the call decision tree function which is the message right over here. So if I select different options, neural network, so it'll call the neural network function, the Bayesian classifier function, or the majority class function. And that's pretty much really like the first step. So in the next week, we'll kind of add in more options to the form, because we need some inputs for all possible attributes that we want to include in our model. So we need like an input for like the age attribute, gender, and so on and so forth. And we'll store all of those input values into variables, and then we'll pass those values as an array to each one of those functions. And in the other weeks of the class, I guess all the way up to the last class, we'll just take those values, and then we'll create a function that corresponds to the export that we've received for a model from RapidMiner, so that we can process those values and then generate predictions within the dashboard. Because there's no better way to understand how these models actually work than going through the basic calculations. And a lot of the work goes actually in towards like training the model. Just taking your exported model and then handling like an input to it is pretty straightforward as far as the coding is concerned. Usually it's a combination of adding and multiplying things, and then you get like an output. Any questions up to this point in terms of what we've covered for today? You excited at all? About as exciting as one can be when dealing with code. Well, that being said, I thought we could spend a little bit of time working on activity number 3. And I do have some requirements for that activity. So let me just scroll down here with the slides so I can show you. Let's go to the last slide. Okay, so the goal for that activity, the aim of the assignment, just to familiarize yourself with Apex charts, particularly their documentation section. And what I'd like you to do is to do not really like a far inference. I mean, it's more like a really basic analogy. So right now you have a few examples of creating a chart for a nominal attribute, numerical attribute. So what I'd like you to do is to use RapidMiner to generate some descriptive statistics for another attribute that we didn't cover so far in the dashboard. So it might be, for example, so far we have gender, we have age. So you could use the attribute like the class, or embarked, or even the number of siblings, or the number of, I always forget, it's like parents and something else. But you can use either one of these 4 attributes, and I'd like you to try to create like a new chart. Oops. Sorry about that. So I'd like you to create a new chart for either one of these attributes. If you have any questions on how to go about doing that, just let me know. I'll come over and help you out. First step though, I mean, you'll probably have to rely on RapidMiner to create your descriptives, or you can actually take a look at Kaggle, and I think it actually like lists the descriptive statistics, at least for nominal attributes, like directly when it describes the data set. So try to generate these in RapidMiner, and then go to the code for that chart. Maybe start by just copy pasting, and then see which values that you have to customize in order to create a new one. And that'll just give you like a little bit of practice in terms of how to create like one basic example of a chart, but with like different values. And then we'll kind of up the complexity there. Like for the next assignment, it'll be like, what happens if you want to create maybe like a different kind of chart to render new values. So that'll be due this Friday, 11:59 p.m. Not October 25th. So by then, I think it'll be November 1st. And once you've done this, just submit the URL to the GitHub repository where you have your dashboard stored. So maybe create like a new repo for like activity 3 and send that my way, and then I'll send back some feedback. So do you have any questions in terms of that assignment? So I would recommend for this assignment to stick with the same kinds of charts. Choose a different attribute. Yeah. So like for P class, it would still be like the bar chart, but of course like the values would have to be changed. You'll have to update the series, maybe the title. Any other questions? All right. Well, get to work, and I'll come over if you have any problems and stuff, and I'll help you out. We should have at least until 12:30 to get that done. And then by then I'll just start talking a little bit about neural networks. Just a heads up, we'll start again in about 15 minutes. If you want to take a break. Gonna want to keep hydrated for the next part. questions before we move on to the next section? Well, you have until Friday to submit that assignment. If you have any questions, feel free to drop by my office in the meantimes, or if you encounter any kind of issues, we can work through them through revising and resubmit as well for that assignment. Otherwise, if you want to follow along for the second half, do take a look at the class slides. They have all the notes, and in fact, you can download the RapidMiner project file, which can help speed up a little bit more later on once we get to that point. But before we do, I just wanted to talk a little bit about neural networks. Just to get some terminology out of the way. And first and foremost, how neural networks are represented. I'm talking about like some of the components. So in terms of the model representation, neural nets are made up of first input nodes, where you may have a vector or an array of values. So let's say you have, like, for example, like a node that represents an attributes like age. So that value might range from anywhere from like 0 to 72, for instance, or like a value like gender, like male and female. So for as many attributes as you have in your classifier, you have a certain number of nodes. And those values are fed into this input layer that makes up the first nodes. These nodes are interconnected to a hidden layer, to other nodes, that are themselves connected to the output layer. And all of the links that interconnect the nodes have certain weights to them. And so the input values in the nodes are actually weighted, which transforms their value for the purposes of prediction. So again, fed through a hidden layer, which again are weighed again before going to the output layer. And at each point, the weight in the links pretty much dictates how the information is kind of transformed. Again, with the purposes of generating better predictions, so reducing error overall in terms of your model. And there's a certain learning process that takes place in order to find the optimal values for these weights. So in terms of constructing the model, so assuming again an input layer, hidden layer, and output layer, each node has a series of incoming links that are weighed coming from other nodes, such as the inputs here, so 1, 2, 3. So the inputs, these nodes in the input layer, are interconnected through links that again are weighed. And in terms of each of these nodes, so there's a two-step process. So calculating the net input as well as the net output of a node. In calculating the net input, there's a certain bias that gets added to the weighed input. So both the inputs that are weighed coming in, so being the sum total of these weighed inputs, so that gets added to a certain amount of bias. And the value for the net input gets sent to a certain function. The functions actually can differ. Some of them, one of them being like either an activation function or a sigmoid activation function, depending, in order to calculate the net output. So the whole goal behind training an artificial neural network is pretty much determining what's the optimal value in terms of the weight that will moderate the values that you get from your input nodes to generate the best possible predictions. And you also want to learn the optimal values for the bias that gets added to those weights, to those weighed inputs. So those formulas pretty much look as like this. So for the net input calculations for one particular node, so the net input being represented by the I parameter here, so that's equal to the sum of the weight time the net output of one particular node. So the net output, like if you're in the hidden layer, for example, the net output would just be the input values that you get directly from your first nodes. So the actual values for like age, for example, or like 0, 1 for a particular type of gender, plus a certain amount of bias. So both the weights and the bias parameters here, these will be learned while you train the model. And the node inputs are typically scaled. So they usually range from like a value of -1 or 0 to 1, as long as the scale is the same for all of the attributes. And I'll kind of talk a little bit about that in RapidMiner, setting that up for data pre-processing step. So the sum of the weights times the now output of previous node plus the amount of bias for the net input. Once you've calculated your net input, which would be the ij parameter, the ij parameter is used here within a certain function in order to calculate the net output. That's the actual kind of prediction that's generated from the node. And in the case of like a sigmoid activation function, so that function could look like this, so 1 divided by 1 plus the natural base logarithm, and then to the power of minus ij, which would be the net input value. And so what will happen is that at this level for your OJ score, the net output, the actual function that plots that score will kind of look like this, where your values have a tendency of ranging from like 0 to 1, and they'll slope a little bit along the like the extreme ranges around here for the tails of that distribution. So net output always going to range from like 0 to 1, basically. So if you're calculating the net output from the output layer, this means that when you're generating a prediction, in the case of like, binary classifications, you have like two classes, either like a value of 0 or a value of 1 that you're trying to predict. So you can set up like a basic rule, establishing like a threshold where you say that the net output values, if they're greater than 0.5, then your prediction is going to be a value of like 1 for that particular class. If the value is actually lower than 0.5, then the predicted value is going to be 0. And typically there's as many output nodes in the output layer as there are classes. So in RapidMiner, for instance, when we train our model, you'll see that there's like 2 nodes at that level. So one for survival, the other one for if the passenger died. And so we'll generate net output calculations for each of these nodes. So if we were to deal with like, let's see, just want to go over like one simple example of how you generate those calculations for the net output, just to give you like a sense for how the model is applied in practice. And so if we assume like this topology for the network, where we have 3 input nodes, so x1, x2, x3. They're interrelated to 2 nodes at the hidden layer, so 4 and 5, which are themselves related to 1 node at the output layer, so node 6. So each of these nodes are interrelated by links that are weighed. So for instance, weight 1 to 4. So interrelating each and every one, so there's weight for 1 to 5, 2 to 4, 2 to 5, and so on and so forth. This means that you can assume that you'll have, let's say, a set of initial input values. So in our case, this might be if you had like an observation for this vector that would have a values of 1, 0, and 1. If we were to build like a network for like the Titanic survival problem, for instance, it might be like an array of like, like 8, or I don't know how many attributes that we have so far, but 10, where you have like values for like the age, values for all the combination of genders. You might have like 3 values for embarked, like Southampton, like 0, 1, for instance. So that's one particular observation that we're trying to classify with a set of values for these parameters. And then you can also assume that your network has certain weight values that are assigned to it. Now those weight values, they'll always change constantly throughout training the network, throughout the learning process, trying to find the optimal weights. But here we're just using, for the sake of calculation, like these are the set of weights that you have at this particular point in time. So once you actually set up your network at the very beginning, all of these weights are just like random values that are initialized. And all the bias values are just set to like 0. But over time, you try to find like the most optimal values for each of these. You'll also notice that the bias values only for the nodes that are assigned to the hidden layer and the output layer. So the bias for like node 4, node 5, and node 6 are just listed here. Any questions so far in terms of those different values? Okay. So first step, in terms of calculating the net input values. So assuming that you have a set of observations, so 1, 0, 1 is your values. The net input calculations, again going over the formula, so the net input is equal to the sum of your weights times the net output of a node, so in this case the actual values, so 1, 0, 1, so the values that we got from that observation, plus the amount of bias that's assigned to that node. So in our case, let's say for node 4, so going through the calculations for that particular case, we have as our bias for node 4 a value of minus 0.4. So if you remember previously, the bias here of minus 0.4 for that particular node in our network. And for node 4, we have 3 interconnecting links. So weight 1, 4, weight 2, 4, and weight 3, 4. So for weight 1, 4, the incoming value here for x1 was actually equal to 1. So for weight 1, 4, the value was 0.2. And we'll just add in that to our formula over here, so 0.2. In the second case though, so for weight 2, 4, you'll notice that the input value for that second node was actually 0. So here if we make 0 times 0.4, so that'll just give you a value of 0, which we've just like listed here. And then for the third link over here, so looking at the weight for 3 to 4, since for x3, that third node, we had a value of 1. So 1 times the weight for that link, so 1 times minus 0.5. So we'll just list this as our value over here, third value. So if you sum total the multiplication between the weights and then the net output of that node, and then you just add in your bias value, so the sum total will be equal to minus 0.7. And to calculate the net output from that particular node, so node 4, you have to add that into your sigmoid activation function. So the net output here is equal to the sigmoid activation function over here, which is 1 divided by 1 plus the natural base of your log to the power of minus the input value, the net input value. So in our case, the net input value being negative, so it'll just be 1 divided by 1 plus e, your natural base, to the power of 0.7, which is equal to 0.332. Now, the net output, because of the sigmoid activation function, will always range between 0 to 1. Now, the same process is repeated again for the net input calculations for node 5. But in this case, since you have different links that are spanning towards it, you have to account for different weight values. So weight of 1 to 5, weight from 2 to 5, and then weight from 3 to 5. So the node value, the incoming value here for that particular node is 0. So in fact, we don't have to really worry about like the second weight, so weight 2 to 5, since that will only be equal to 0 anyways. But for both of these values, x1 is equal to 1 and x3 is equal to 1, we'll have to multiply these with weight 1, 5 and then weight 3, 5. So going over here, weight 1, 5 is minus 0.3. Weight 3, 5 is 0.2. And then the bias at that particular node is 0.2. So in terms of our formula, minus 0.3 for the weighted input for the first node, plus 0, which is the weighted input for the second node, plus 0.2, which is the weighted input for the third node, and then adding in our bias at the very end over here. That'll be equal to 0.1. So after you've gotten the net input, you can just plug that into your sigmoid activation function to calculate the net output. In this case, it'll be 0.525. So going back to our network, we only have to calculate the net output for this particular node here in the output layer. So in this case, we have to take into account the net output for node 4 and for node 5. Have to weigh that node output considering the value for the weight from 4 to 6 and then the weight from 5 to 6. Now our node output our net output calculations we've already obtained. So 0.332 for node 4 and then 0.525 for node 5. So you'll see those values being listed here below. So 0.332, 0.525. But these are multiplied by the link weight value. So minus 0.3 in the case of the weight spanning from 4 to 6. And then here the net output, 0.525 times 0.2, which is the weight from node 5 to 6. You add in your bias value for node 6, which would be 0.1. And that'll give you a value for the net input of 0.105 minus 0.105 for node 6. Plug that into your sigmoid activation formula, and the net output will be equal to 0.474. So again, assuming like a very simple rule of if the value falls below a threshold of 0.5, the prediction at the level of that node is that for whatever class that the node represents, so we say that the prediction will be like false. So if the node would be like survive in the case of the passenger model, then we would just say that the prediction, well, it seems as if they were actually like more likely to like die in that case, because the likelihood of that outcome is lower, considering like another possible outcome. So that's just a simple example of how the model can be applied to classify like a new observation. So if you have new net input values coming into the input layer, so all of those input values get weighed in terms of the net output calculations at the hidden layer value, and then weighed again to get at the output layer to generate your predictions. Does that kind of make sense in terms of the calculations? It's a little bit kind of tricky to keep in mind, and honestly, I mean, the slides, I could have maybe broken down a little bit simpler. The hierarchy behind this thing is a little bit much to keep track of. But I'd recommend just to kind of sit down with the slides and maybe even like pen and pencil, like go through the steps of like calculating it. We'll also revisit it a little bit later once we write like the JavaScript function to do exactly that. I mean, how do you handle like a new observation, classifying it to generate those predictions? So those simple calculations kind of assume certain things, like that you know what are the weight values and that you know what is the best bias value to kind of moderate and weigh the input values. But in an actual scenario, I mean, we don't really know these things. At the very first moment when you train a neural network, the actual weights that are assigned are just like randomly chosen. So it's just a set of small random numbers that could range from like anywhere from like -1 to 1 typically. And the bias will just be like set off at like a value of 0 to start off with. But during the learning phase, so the network will just gradually learn by just adjusting ever so slightly the weights and the biases in order to be able to generate better predictions for your class labels, considering like what you've actually observed. And so you need to have like a training set that's labeled. The model will try to do predictions, and then whenever it generates the predictions, it'll calculate like what's the error? Like, was the prediction like off? Was it exactly the same as what was observed? And then through a process that's called back propagation, it will take the error and then will portion it back to the node's weights and biases to make small little corrections. And it'll do that like hundreds of times. So it'll try and predict, adjust a little bit, and then again try and predict, adjust a little bit, and then so on and so forth. It's called back propagation because typically the direction for that process of adjustment is like goes like backwards. So like you calculate the error at the output layer, and then you make adjustments first through the hidden layer, and then down back to the input layer, like adjusting the weights at that level. So a little figure to explain like how that happens, like at the output layer, you'll calculate for the error, making adjustments, kind of working your way downwards towards the network. Again, calculating the error here at these levels and then making adjustments as you go on backwards. Now, to actually see and simulate that process, you don't need to know all the details, but it is helpful to understand it from the point of view of like what happens when you make certain choices for model hyperparameters. So I've listed here like all the formulas. So first, in terms of calculating the error for the output layer, and then the error for the hidden layer, and then how that error gets back propagated to just make adjustments to calculate the new bias value and then the new weight values here to the left. So starting off with the first formula for the output layer. So the error is equal to the net output of that node times 1 minus the net output. Get a sense for like how much discrepancy that there is. Times t, which is equal to the actual observed class outcome. So let's say that you like predicted like 1 that they survived, while the actual outcome could have been 0. That passenger just died. And so t will represent that value, either 1 or 0, depending on the actual observed class that you're trying to predict. So t minus the net output calculation for that node, and this will be the error calculation for the output layer. Now at the hidden layer level, you have to take into account the error of nodes that are part of the output layer. So it'll actually be the net output of that particular node in the hidden layer times 1 minus the net output, and then times the sum of the error of the nodes in the output layer times the weight that interconnects the node in the hidden layer to the one in the output layer. So the weight error. So just to illustrate that process before we move on forward to talking about like the new weight values here. So if we again revisit the same network, so assuming the same topology, so one output layer with one output node, very simple. So 2 nodes here in the hidden layer, and then 3 nodes in the input layer. So first, starting from node 6, so in the output layer, you have to calculate the amount of error. So we calculated previously a net output of 0.474 for that node. So times 1 minus 0.474, so the net output again for that particular node, times the t parameter, which is equal to 1 in that case. So the actual observed class that we're trying to predict for that particular observation was a value of 1, so meaning that the class was assigned, so it could have been like survived, in this case, was like a value of 1, so true. So 1 minus the net output of that node, and that'll give you a value of 0.1311 for your error. So now that you know the error for node 6, you have to take into account that error and then weigh it, considering the values for the weights for each of these links. So links spanning from node 4 to 6, and then links spanning from node 5 to 6 as well here. So these have values of minus 0.3 and minus 0.2. And so if we were to use this formula here to calculate the error for node 4, for node 5 and 4, so let's do it in order. So in terms of the net output calculations that we obtained in the previous step for node 5, so that was equal to 0.525. We do times 1 minus that same value, but times the sum of your error multiplied by the weight. So here we already calculated the error at node 6. So we take that error value and then multiply it by the weight. In this case, it's here for node 5. So weight from the node 5 to 6 is equal to minus 0.2. And so 0.1311 is here times minus 0.2. And that will be equal to this value. So repeating the same steps again for node 4. So the net output of node 4 that we calculated the previous step, so that was equal to 0.332 times 1 minus 0.332 times the weight error of the node here in the output layer. So the error here being 0.1311, we just multiply this by the value of the weight for that link, which was minus 0.3. And doing so, you can calculate the error at the level of that particular node, so minus 0.0087. So typically, the first step before calculating the new weight value and the new bias value is to just get your error rates at each nodes. So both of the output layer and the hidden layer. Since you'll need these values for calculating the new bias value and the new weight value. Now for the new weight value, calculating the delta and the weight value here, so just essentially like the change in the weight. So that's equal to the learning rate, which is represented here by the L coefficient, and that's just a constant value that you assign. So that's like a hyperparameter in the model. So it's already predefined. You define it. It's kind of like any value that you want, really. What you have to be mindful of is like learning rates. If you choose like a small value, you'll only make like little tiny tweaks to the weights within your model. And so the learning rate will it will take a little bit longer sometimes to reach like an optimal value. If you assign a learning rate that's too large, then you'll make like large tweaks to the model. And so the process for learning and trying to find the right predictions might be a little bit more erratic. So we'll talk a little bit about that process when we try to like optimize for some of these parameter values and justifying your choices. Typically, like here I've listed as like a constant of like 0.9. Default value for the learning rate is actually much smaller. I mean, it's usually somewhere within like 0.01, in fact, if you're using it with like a momentum parameter. So some of these choices that you assign for these values for these like hyperparameters, they kind of have like a really large impact in terms of how well your model will fit. So like the calculations, like you don't have to like recreate it yourself. You just have to understand like exactly like what that parameter is being used for and what impact that will have towards like the learning process. So assuming like a constant value here of like a value of like 0.9. So that will be multiplied by the error of that particular node times the net output of that node. So if I can clarify that again, because I have to be careful about the language here. So the learning rate multiplied by the error of the node at the output layer times the net output of the node in the hidden layer. And I'll kind of like give you like a more visual example of that. So for the new bias value, that one's a little bit simpler. So it's just like the learning rate times the amount of error that you have at that particular node. So for an example of these calculations, so if we take our case here where we've calculated the error here at node 6, which was equal to 0.1311, we have the weight that was assigned at that particular link, which was equal to minus 0.3. And then we had our net output calculation for node 4, which was equal to 0.332. Now the bias value at node 4 was also equal to minus 0.4. So let's say that we were to update the weight for the link spanning from node 4 to node 6. So plugging in our values in the formula. So first we'd have to take into account like what was the initial weight of that link. In our case, minus 0.3. So that's the weight that we're starting off. And here are all the values to calculate the delta of that particular weight, so the extent at which we want to change it. So first, plugging in our first value, our learning rate, which is a constant, so 0.9. Next, multiplying that by the value of the error at the node in the output layer, so node 6, so that would be equal to 0.1311. Times the net output calculation for node 4, which would be equal to 0.332. So when adjusting the weight, we take into account the extent to which we actually want to make modifications to it. We take into account the error that was made in the step forward here, as well as the node output calculation that was made there. And so the new weight that gets calculated through that formula is minus 0.261. So just like increasing the value of the weight a little bit. Now for the bias calculations, and I think that's the bias at node 4, that particular node. So again, that's equal to the original bias value for that node, which was equal to minus 0.4. So plugging into our formulas the learning rate, so 0.9, which is the extent at which we want to modify it, either like a little bit more or a little bit less. Times, here this was, what was that? The actual error for that particular node. It's not listed here, but it was calculated at a previous step. So minus 0.0087. You'll remember those calculations from node 4 over here at this step, so minus 0.0087. So here for the bias calculation, we'll just take into account the amount of error that was made at that particular node. So kind of disregarding everything that's happening on with the node, the node in the output layer previously. So just taking into account the error at that node and then the learning rate, so for the extent at which we want to modify it. And so in this case, so that'll just be equal to minus 0.408. So just like a slight little decrease in the bias value. So when you're training your neural network, it'll do this like hundreds of times. I'll just do like small little tweaks, increments or decrements in values. Hopefully at the end of the training, try and get at better predictions by just taking into account the amount of error and then making corrections for it. So there I've listed all the calculations for all the weights throughout the network, as well as all the bias amounts, but I'll let you go through these details. I mean, it's just really important to understand exactly how the learning rate is being used, since that's the decision that you have to make at the very beginning before training your neural network, is what kind of value that you want to use for the learning rate. Another important thing to keep in mind is that typically when training a neural network, you want all of your values for both nominal attributes and numerical attributes that'll be represented as nodes in the input layer to have the exact same scale. So the scale doesn't actually matter, like the scale values. It can range from like 0 to 1 or from like -1 to 1. But you do have to normalize those values. So for nominal labels in the training tuples, for example, you can convert them to binomial scores. So if you have like an attribute like embarked, embarked in our Titanic data set has 3 different values: Southampton, Queenston, and somewhere else, don't quite remember. So all of those can be assigned values of 0s or 1 to convert them from nominal attributes to binomial attributes so that you can use them within your network. Now for numerical attributes, the same thing, you can use a min-max normalization to change their scale values. So like age, for instance, might range from like 0 to 72 in your data set, but you can convert it to different range of values so that it ranges between like 0s and 1s. And I'll show you an example of the pre-processing steps that you can apply in order to recreate that. There's also an inner normalization operator within the neural network that you can just like select, deselect, and I'll just convert all of your values from scores that range from like -1 to 1. And to give you an example of this, so I'll actually switch off from the in RapidMiner, so I can show you data pre-processing wise how you would set that up for your analysis to go about training a neural network. So if you open the week 7 project file, in RapidMiner, and you open the data pre-processing operator, and then navigate at the very end to feature selection over here. So for the third option, I've listed here a few additional steps for data pre-processing for neural networks. One of the most important for these is the converting the nominal to numerical attributes. And so that's just a dummy coding all of your nominal attributes to scores that range from 0 to 1. So here I've also listed like a few additional options. So I converted that again for like the target attribute here for survival, just using like to survive equal yes value. But to give you a sense for what that looks like, I'll just add a breakpoint at that step so we can take a look at the actual output. So you'll notice that it converts by dummy coding nominal attributes. It'll take a nominal attribute like embarked. We'll just add in a statement like is embark equal to Southampton, or is embark equal to Cherbourg, or is embark equal to Queenston. Each of these 3 attributes will be represented as separate nodes within the network, and then they'll always have either a value of like 0 or 1. So they're scaled all on the same original scale. Now you can also do a min-max transformation to your numerical attributes to change the range of those attributes. Step using the normalize operator here. And then just specifying that here by value type, let's say, all the numeric attributes would be transformed using a different range from values that range from 0 to 1. Now I can give you the exact formula for how that's done. If I remember correctly, I'm not going to try and do it by memory. But it maintains pretty much all the same directions, all the same differences between the numerical scores. So the range is exactly the same. So if you were to have if you were to be 72 years old, your new value for your transform attribute would be close to 1, since that's the maximum score. If you were to be close to 0 in age, then your new value would be 0. So the minimal value. I think it's something the maximum plus, I won't try it. I added it in another example and stuff from a previous project, and I'll just share that along in an email or something. What that looks like in terms of the output is, I don't actually have age as an attribute there for whatever reason. But if you look at something like fair that used to range in between 0 to 300, now ranges from 0 to 1. So it doesn't really matter the exact scale, just as long as they all have the same scale. That's the important thing when training a neural network. You don't want these little extreme values, outliers, to kind of trip up the learning process. It'll cause really erratic behaviors when you recalculate the weights and the biases, and sometimes it'll cause some problems in terms of the fit of your model. Now it gets a little bit more complicated for normalizing your scores when you're using something like a cross validation or a split validation to validate your model. And to kind of facilitate with that, what I usually do is I recommend to just kind of turn off normalize operator over here. You can still dummy code all of your nominal attributes, but then when you're using the neural network operator, just remember to click the option of normalizing your scores. So if I go to my data processing, and here I'll just jump right into the optimized parameter option, into split validation, into train model. And you'll notice that one of the options for the neural network operator, if you select it, is to normalize your attributes. So just make sure to select that option. I recommend normalizing within the operator for the model itself. It'll use a scale that ranges from -1 to 1. So it'll convert your dummy-coded nominal attributes from -1 to 1 on that same scale. Same thing with the numerical attributes. But more importantly, it'll normalize within the split. So whenever you're validating your model, you're splitting all of your data sets into a training and then into a validation set. So because you don't have necessarily all of the observations within the training set, the maximal value and the minimal value is likely to be different. That's important to take that into account, because when you're normalizing, you're taking into account the minimal and maximal range of those values, and then you're converting it to another range. So it's always good when you're training a neural network to normalize within that particular fold. So if you're doing a split validation, for example, to actually do this correctly, I would have to normalize here within the training view of my split validation. So that I only normalize or standardize for that effect within that particular split or fold if you're doing cross validation. Just a little quirk of working with the neural network. So for all intents and purposes, dummy code your nominal attributes, and then make sure that you select normalize when you're using the operator, and then you should be fine. It's one of these little things that's kind of tricky because you can't actually see that come into play, and sometimes it'll cause some little errors. So what I did want to talk about also is how to go about optimizing for choices that you make relative to these hyperparameters. There's quite a few different parameters that you can choose when you're training neural networks. So the first of which is the number of hidden layers. By default, it'll just create one hidden layer, with about as many nodes as there are input nodes. You can change the topology of your network by adding more nodes within your hidden layer, or by adding like extra layers if you wanted to. I mean, at some point, if you add in like 5 or 6, I mean, it'll take a long time to train. So do be mindful of that. And typically by default, I mean, you just kind of stick with like one hidden layer, or maybe like 2 really, to see if there's like any benefits to it. But again, like the topology of your network, you can optimize it by just like modifying. Like if you were to like add in like some new layers here, the default there is just like 2 for the layer size. But here I can just say like I want to add in like 6 nodes for the first hidden layer. Then for my second hidden layer, I like to have something like 5, for instance. So if you can get into these like more complex scenarios where you can modify the topology of your network to see if you're able to capture any different patterns through some of those choices. Another hyperparameter that's important to consider is the amount of training cycles, or like the learning epochs, when you kind of like read about like neural networks. And that's just like the amount of times that you back propagate error throughout your network. So if you do like 200 times, well, it'll just go through that process like 200 times, and to make small little modifications to the weights and to the biases to hopefully improve your predictions. So you can increase that amount, you can decrease it. If you decrease it, you run a chance of your model underfitting because you just haven't corrected for the error enough. If you do it too many times, well, then you'll just keep on training your model and adding to the length of that process without having any kind of benefits, really. I mean, to some extent, you might overfit your model, but that in our current setup, we can't actually evaluate that because we're only calculating error for the validation set. There's also some additional parameters here for learning rate and momentum. I'll show you the formula for that on the screen. So the learning rate is that L parameter that you saw previously that just specifies the extent to which you want to adjust for the delta value in both the weights and the biases. So if the learning rate is too small, well, learning might occur at a very slow pace. If it's too large, then you might oscillate between inadequate solutions. One way to kind of picture that process is to, let's say that you imagine on the x-axis here that you have like a certain amount of training cycles that might range from like 0 to 200. And then you're adjusting for your weight value over here on the y-axis. Every time that you make like a certain amount of changes to these little parameters, you'll see like little variations in terms of your error. And sometimes you'll reach a point where the error is kind of pretty low. But then if you were to train a little bit more, you'll get even better results. And what these hyperparameters try to avoid doing is getting stuck in what's called like a local minimum kind of solution. So it means that like, hey, you've seen like some decrease in error here, but it's not actually like the best solution. Like the global minimum is actually over there. And so what the learning rate is doing is just like making like small little adjustments to kind of test for different kinds of possibilities in terms of that decision space. Make sure that you don't get stuck in the suboptimal solution. So that you can actually picture by optimizing and just like running your model for making like every time making like slightly different decisions to see like what's the end result. I'll show you an example of how to set that up in RapidMiner. But the same rationale applies to the momentum. Momentum is just like another kind of correction that you're making. So in this case, for instance, once you've calculated the delta for the weight, you can just multiply the momentum value here, which is usually around like 0.9, directly with the previous node weight, to again to try and make some adjustments. Now the next parameter that you can choose here to apply is a decay. The decay will just progressively reduce the value of the learning rate over the amount of training cycles. So again, with the idea that you might start off with like a really large learning rate to oscillate between extreme solutions, but then at the end you might just gradually converge towards like an ideal. So just choosing to like minimize the amount of learning rate or adjustments here that you're making to the weights and the biases. Shuffle is another strategy you can use to avoid getting stuck in like a local minima. So that's just like training the network over like a subset of observations and then just like changing the observations for every training cycle. So with like slightly different observations, so it'll just calculate the error and adjust differently for each and every one. And sometimes that can help with like avoid getting stuck in like a suboptimal solution. You can specify a stopping criteria here for error epsilon. So if for each training cycle, if the amount of error gets below 0.0001, so it'll just stop the training process so it doesn't get like too lengthy. And here for the local random seed, so that just specified the local random seed value that's used to calculate the initial weights. So if you use like a different local random seed value, your model will just be initialized with a different set of weights, essentially, just random numbers at the very beginning before going through the learning process. So typically when you optimize for something, you can like modify these values to have at the very beginning of the training process just slightly different kind of like networks with like different weights assigned to them, just to see like what's the variability in your outcomes. So all of these operators I've set up in an optimized parameter grid operator over here. And that's directly within the data processing step. And so you can click on the edit parameter settings here. And then you can drag in different parameters that you want to test for as part of your optimization. So by choosing neural net, you'll have access to all of your parameters list, hyperparameters like the amount of training cycles, the momentum, the decay, and so on and so forth. You can select these and then drag them to the right. And also select the values here to specify like what the minimal value that you want to train, that you want to test for, what's the maximal value, the amount of steps to take, so the amount of times that you want to interpolate the values, and then the type of function that you want to use, if it's like linear, or quadratic, or logarithmic. So if I choose here, for example, like the learning rate as one parameter to optimize for. So here for my minimal value, I might assign something like 0.0001. And then a max value here for the learning rate of, choose something that's 0.5, let's say. So if I take 10 steps between those values using a linear scale, linear function, so that'll test with like 0.0001. Actually, like add that here so you can see it. So 0.001. Next, I'll test for 0.051, then 0.101, and so on and so forth. And I've also specified here using the local random seed parameter of the neural net. And those values usually range from like 1,000 to 2,000 for a seed value. So you can just add that in, 1,000, 2,000. And 10 different combinations of those values. So using these optimization parameter operators, since this is a grid search process, it'll test for every possible combination of learning rate values and local random seed values. And so it'll train the model like for 121 of those different combinations. So if I click on OK, And just make sure to click on the log performance and the log all criteria options here for your checkboxes. And before I start that process, I'll just double check, make sure that I have everything set up correctly for my momentum 0.9. The learning rate here will just be modified through the optimization process, and this value here will also be modified as well. So if I just run this, so here I have a breakpoint set up for the data pre-processing step, which I think this should be okay because I'm normalizing anyways at the neural network level. So click here, so everything has been demi-coded. And you'll see in the logs, so there's two logs. So I use the log operator here in the validation of that split validation, so in the validation view, so it's just logging the error for each and every combination of values. But here you get like all the details. And what the what the optimization is doing right now is just like maintaining the value for the local random seed to 1,000. And so the neural network will just be initiated with a set of weights. So it'll try to train a network using a learning rate of 0.001, then 0.051, and then 0.101, and so on and so forth. And then we'll calculate the error for that network. So the question is there like a trend that would emerge that would kind of suggest what's the ideal value for a hyperparameter? You know, you can use the default values, and usually it just works fine. But most often, like, you might have a reviewer that comes up with, like, you know, if you choose a learning rate of 0.01, like, how did you choose that number? So if you can't, like, offer like a citation to kind of say, well, this is just like a good rule of thumb, you can always optimize for those values to just say, well, we've empirically tested for all possible combinations, and this is the trend that we've obtained. And, you know, just like report a graph. The training process will take a little bit of time, which is for class circumstances. But if you take a look at the data processing operator, you'll see that there's like a little progress bar that shows up over here, where I'll just give you like the amount of like percentage complete. And in our case, we're just working towards like 20% right now for that particular analysis. And so in some cases, you'll have to wait a little bit. So just be mindful of the choice that you set in terms of the ranges. So if you test for like a lesser amount of combinations, it'll take like a lesser amount of time. But what you'll get typically are graphs that kind of look like this. So for the learning rate, on the x-axis, so learning rates ranging from 0.001 to values of 1. You'll see that if you actually set the value for the learning rate to no value, you'll get some of these extreme results here. And this is on the y scale, is the actual error on the validation set. So when you apply your model to your data set and you try and make your predictions. So if you don't adjust for the learning rate, what you see are errors as high as 0.376, which is not very good. But using a value of like close to like 0.01, like the default value, you actually see like far lesser amounts of error, like the absolute scores, and far lesser amounts of variations too, as opposed to if you use like larger learning rates. Like you'll see here like values close to 1, like you'll see like some of these spreads in your values that are obtained. So again, just using, you know, not too small a value, not too large a value, and just being mindful of those choices, it can have a pretty large impact in terms of the fit of your model. So if your momentum value, for example, is too large, so you're more likely to get stuck in these local minima, so those suboptimal solutions, where the error here is just like much larger than using something a little bit smaller. here in terms of the training cycles. So varying the training cycle from 0 to 1,000. If you don't let your model, if you train your model only over a few cycles, you'll see that the error is quite larger compared to if you allow it to train a little bit longer. So ideal values ranging from like in the range of like 150 to 200. Where any more than that, I mean, there's just like no clear benefits. And so let's see where we're at with the current analysis. So we're up to 40%. Is there any questions so far, though? Well, in terms of working with neural networks, really important to be mindful of that data preprocessing step. Just remember to dummy code all of your nominal attributes. Check the option for normalization within the neural network operator. And some of these parameters using a grid, really great stuff. I mean, you can easily test for a range of different combinations of choices. So that way you never have to assume anything. You can just guide your choices based on the data, which is always best. So just another technique, other than the split validation technique, which we're actually using within the optimization scheme. So here we're splitting the data set to training and validation set using 60% of the data for the training set. But next week we'll talk about a little bit more, I think, about cross-validation, and we might also talk about resampling. And here I'll just a little bit, or I might actually be able to graph as it's running. Yeah. So the way to actually picture those results, so if you go to simple charts and the results for the optimized parameters grid where it logs all the results, on the x-axis you can plot whatever parameter value that you're testing for, in this case the learning rate. On the y-axis you can plot for your error, the resulting error on the validation set. And for your color column, choose a local random seed, which is, again, these values we're modifying through the optimization. We're just using slightly different random seed values to initialize the network with different weights. And you can also use like some jitter here. Sometimes you'll see that the predictions, so some of the cases, the observations that you're making actually overlap on top of each other. So using just a little bit of the jitter, we'll just kind of change the position slightly so that you're better able to see it. And I mean, in this case, might be a little bit too early to get some good results here because the distribution is all over. You have like a lot of variability for all the different values, but clearly the error rates that you get in terms of the smaller values, which I think was like 0.00 or 0.01 in that case. No, it's definitely 0.001. Much smaller, they're more tightly grouped over here than the cases when you read into like some of these values. And the difference is actually practically meaningful. I mean, if you're talking about like an error rate of like 0.16 all the way up to, in these cases, 0.23. So a 20% error on our validation set, which would be roughly in that case 40% of like 800 examples. I mean, it's quite a bit. Can't come up with an actual number though because the math is hurting my head, but again, the idea being that it's always best to optimize for some of these hyperparameters rather than just choosing, you know, what they recommend from the textbooks. And I'll kind of keep that running. But do you have any other questions so far in terms of using either the optimization option or working with neural networks? Alright, great. Well, I mean, it's one modeling option. I'd recommend to try with decision trees, you try with neural networks, you see what works best. Some cases you might find like little benefits towards using one approach rather than another. But once we've trained our models, now talking about the coding, I'll show you how to like deploy them. So once we've got the output, which kind of looks like this, the output for a neural network, usually you have the description of the network that's listed here at all of the nodes. So you have like node 1, node 2, node 3, node 4, and so on and so forth, as well as the output nodes. So for class false, for class true. Now the amount of bias is actually listed here at the bottom, so bias, or is listed as like threshold. And so here, if you click on this like visual graph, for example, you'll see that like for the first node over here, the weights, they're all listed for the incoming links with like your bias value over here. That's exactly the same information as you'll see in the table over there. So this means that the weight that's incoming from your first node, which would be embark equals Southampton. So the node over here, embarked equals Southampton, has a weight of 0.105, so after training. And so when you write up the code in JavaScript to deploy that model in your dashboard, we'll just like store all of these weights as arrays, and then we'll have like a little function to kind of do the multiplication, like the node input times the weights to calculate the net input values. So pretty much everything that you need to deploy your model is available in that output. And over here for the split validation performance, that model has an accuracy of like 83.71%, which is not bad. So that's actually like 83% of the observations are correctly predicted by that model. So with the confusion matrix here, where you predict for false values, what you actually observed were 212 observations that had value of false assigned to it. Predictions of true values, so the actual values that you observed was 86. However, in 50 cases you predicted that a passenger died, and in fact they survived. Same thing here, so you predicted that passengers survived, 8 passengers, but in fact they died. But overall that model actually performs pretty well. So, with that being said, we'll revisit this a little bit later. So once we deploy our model in the JavaScript to generate those predictions. And next week, I'll talk about Bayesian classifiers. So again, like just a different representation, so different method for going about generating predictions. It will actually be a little bit simpler in the case of Bayesian classifiers, but still kind of based on some of the same assumptions. I'll talk about different kinds of methods for going about training the Bayesian classifiers. So we might talk about actually cross-validation, resampling, and wrappers all in one class in that case. So if you have any questions working on your activities, just let me know. I'll be around. You can just send those along, and I'll be due on Friday. But I'd say that there's also some homework. So if you take a look at the Canvas class website, I think I assigned one module in Code Academy on conditional statements, so if-else rules. And there'll be a textbook chapter on Bayesian classifiers that you can skim, just give you a sense for how to work with those in RapidMiner. So if we don't have any more questions, well, we can just adjourn and meet again next week.